Yeah, or speak now, or wait, don't speak now. Forever hold your whatever.
Okay.
We'll wait a couple minutes. There's still definitely a trickle of people coming in. Great attendance.
Let's see if I can actually see this while I'm talking. Best one I did was somewhere where the display for the speaker right in the front. You just like stand there, like it didn't block the audience at all. Tend to be looking at the audience and actually look at yourself.
Do you want lights behind there for the?
If people ask me, I don't know.
Okay.
Sure, people will know.
Let me see if I remember how to do this. Is it this one? Yeah, that's not it. Are we expecting anybody else? So, for example. Great. Well, it's my pleasure to introduce today's colloquium speaker, Theo Johnson-Freyd. Theo, I've known Theo since 2007. We went to Berkeley together with Angie as well. We're all graduate students together. And after that, you did a postdoc at Perimeter Institute.
So was it Northwestern?
Oh, Northwestern, and then Perimeter Institute. And he's currently he's at Dalhousie University, joint with Perimeter Institute. And he currently he's a part of the large, Simon's collaboration in global categorical symmetries. It's a very cool, very big grant. And some of his most recent famous work is the proof of the minimal non-degenerate extensions for, I'm blanking on it, supermodular categories.
Slightly non-degenerate.
Yeah. Anyway.
We can do the unitary supermodular version. We can't do we never actually got the non-unitary supermodular.
Great.
That should be a technical problem. It's like a graduate student. Okay.
Today you'll tell us about higher algebraic closure.
Okay, thank you very much. Thank you for the invitation to Dave and for the very nice introduction. Thank you all for coming. There's the absolutely most important thing for me to say in this talk, because I've forgotten to say it every once in a while. Everything I'm going to say is joined with my fantastic collaborator, David Reuter, and everything's in progress. I think, I'm probably not going to get into enough technical details for it to matter right now, but our story, we're quite confident of everything. We have all the proofs written in emails. We do not have any of the proofs written in a tech document. And so, I mean, something's wrong probably, but that's where we are. I also gave a more technical version of this talk. You can read my slides if you want to ignore me. And I give a more technical version at the UC Institute, so there's slides there that you might want to read. So it talks about higher algebraic closure. And rather than dive completely in immediately, I want to sort of start with an actual mathematical physics problem in some sense. How do you talk about the mathematics of closure? Because for me, one of the reasons to do this project was kind of about quantum field theory. So if you have a quantum field theory, whatever that is, it doesn't really matter what it is, because I'm going to ask a kind of cartoon version of a question in quantum field theory. But whatever a quantum system, a quantum field theory quantum system of matter is, it could have some particles, whatever those are. And while maybe this should be an undefined notion, but what you might ask in some sort of setting you're doing, maybe particles are fundamental particles in your quantum field theory, maybe they're the quarks or something in your sort of standard model physics, or maybe by particle I mean kind of particle-like excitation in an effective field theory. These are all types of questions you can ask. And the question I want to ask is there a consistent way, given a quantum field theory, given a kind of quantum matter system, is there a consistent way to assign to every particle a Hilbert space of internal states? Well, sure, I could just assign the one-dimensional Hilbert space to every type of every particle. That would be sort of consistent, but really dumb, because it wouldn't tell me anything. So let me make the problem a little bit harder. I want that my assignment should behave well with all the basic operations I can do with particles. Because as a quantum system, particles can, well, quantum systems are kind of really interesting because you can have superposition, meaning that you could have a system where the state of the system is either a state of particle type A or a state of particle type B. And in that case, I want my assignment to assign the direct sum of Hilbert spaces, because that's how it works in quantum mechanics. And also particles, you could take two particles near each other and you can fuse them together. And the joint system might then decompose as a direct sum of indecomposable subsystems. And I want that fusion to be matching with tensor spaces. And actually, I'm never going to say the word Hilbert again. I'm an algebraist when I'm a mathematician. So by Hilbert space, I really just mean vector space. So here's the question. Can I consistently assign to every particle a vector space in a way that behaves well with kind of tensor product, pretty much? And you can say this in terms of categories if you want. I'm asking there is a category of particles. The objects are just particle-like excitations in your system. The morphisms are ways that particles can move around. I'm asking, does this category have a nice functor to the category of vector spaces?
By relaxing to vector spaces and isomorphisms, do you lose anything?
No, it does not change the problem at all. In fact, you can always upgrade it to the unitary problem. But this is already a problem you can ask in vector spaces. And the answer is no, just flat no. You cannot do this. You cannot consistently assign vector spaces to every particle in a way consistent with fusion for a really simple reason. You pick up some proton or some electron. You pick a proton, and you can imagine arranging a proton in some specific pure state of your choice. Actually, let's take two protons and let's just arrange them in the same pure state. Well, there's a process I can run, which is to just leave them where they are. And there's another process I can run, which is to switch their spots. And if I could do this assignment, then those two pure states should be represented by vectors in the Hilbert space. And so the process that runs that just leaves them here versus the process that leaves them there, those should be the same process at least on this joint, this pure state. Maybe they do different things on other pure states, but on this pure state, they should be doing the same thing. And so I could set up a two-slit experiment where there's where one of the slits is to leave the two protons the same, the other slit is to switch their spots. And this two-slit experiment, those two slits should interfere constructively. And they just don't. They interfere destructively instead. So in other words, what I'm saying is that for protons in sort of the same pure state, this operation of leaving them still is minus the operation of switching them, which is just not how it works in vector spaces. I mean, in some sense, what I'm telling you is something you all learned if you ever took a quantum mechanics class. It's that you can't take protons, and you can't have a sort of two protons in exactly the same state. And this is why, because they would interfere destructively if you. So we do a cheap fix. I couldn't do it. I couldn't assign a vector space to every particle. So I will just decide to change the problem. And instead of assigning a vector space to every particle, I'll just create a new notion of vector space. I'll call them super vector spaces because they're kind of crazy. I think this was due to Dirac. And all a super vector space is it's a pair of vector spaces. Call it a Z2 graded vector space if you want. It's a pair of vector spaces. And the tensor product of them is just you add the gradings together. And the only difference between super vector spaces and pairs of vector spaces with Z2 grading is that you just declare that when you switch things, if they're both in the odd grading, you pick up a -1s. You just build that into the definition of what switch means. It's like you change what the word commutative means. It's not completely clear that this is a consistent thing you can do, but it is a consistent thing you can do. You can develop a whole sort of theory of algebra where the only difference is what commutative means, what the commutator is. And that you would at least have to do to be able to accommodate the problem on kind of simple problems. And now there's no reason why this should be enough. Like maybe there was some other problem, and maybe if I sort of thought a while, I could give you some other. So now you could like you should right now expect that maybe there's like crazy particles that have other types of weird behavior than just this kind of basic Pauli exclusion principle. And now there's a sort of crazy theorem, an actually hard theorem, Zeta-Zeleny from 2002 roughly, that says that this is all you have to do. So Delen's theorem says that if you take, what he proves is just a theorem in category theory, but sort of interpreted in this language, the theorem says that if you have any collection of particles in a quantum system with, which is not the zero collection, and which is not too crazy big, like there's some size constraints on the collection, then you can always consistently assign a supervector space to every particle in a way consistent with fusion. And this is true in enough dimensions. If you're just in 2+1 dimensions, then particles, when they move around, they can grade in interesting ways. But in at least 3 dimensions, the process that switches this way is the same as the process that switches this way, just because you can, sorry, let me do it this way. If you switch around this way, that's the same as switching around this way by that. So this was the sort of problem, this was the version of the problem I want to solve for particles, for sort of 0+1 dimensional objects. And I really want to solve this in high dimensions, but there's this thing that's really a valuable tool, which is, I think it's called the power of negative thinking. Whenever you have a problem that you want to do sort of 0, 1, 2, 3, and so on, you try it at -1 first. Next. So now I'm going to go to -1+1 dimensional physics. So let's step back and ask ourselves a similar question. So in a particle, I mean, I said it was a 0+1D thing, but in a quantum system, particles are really, from the sort of perspective of quantum field theorists, particles are one-dimensional things because they trace out lines in space. There are zero-dimensional things. These are sometimes called instantons. They're sometimes called point operators. Particles are also called line operators. These are just the same words. A line operator, you call it a line operator because if you take a particle and you have so an operator in a quantum field theory is a thing that you can insert at some point and measure something, and it's the value of, like you measure expectation value. Of course, the value of that, the expected value will depend on where you do the measurement. The expected value of the temperature near a fan is different from the expected value of the temperature somewhere else. And so a point operator is something who you measure at a point in space-time. A line operator is something that you measure along a curve in space-time. And for any particle, there is a line operator which just takes the particle, walks it around the curve, and like asks how much work it took to do that, because it's moving through some ambient medium of forces. So anyway, you can ask the same problem. You can have to take a quantum system and have some local operators. And now I want to ask, is there necessarily a consistent way of assigning to every local operator just a number, a real number, that's consistent with the rules of kind of fusion of local operators, multiplication of operators? And I lied slightly. I don't really want to do this for all local operators. Let's just try to do it for the integrals of motion, for the operators that don't depend very much on where you place them, operators that kind of commute with the time evolution. And the reason for doing that is because if you're integrals of motion, then moving the location of the operator doesn't change its expected value. And if I'm at least in 1+1 dimensions, then I have enough room to move operators around and see that the algebra of local operators is commutative. So all I'm asking is a basic problem in undergraduate algebra. I'm asking, given a commutative algebra of local operators, can I consistently assign, is there a homomorphism to the real numbers? And why reals? Because the world is about real numbers. Like the distance between us is a real number. All the measurements you make are real numbers. And the answer is just plain no. You cannot always do this. If you take a superconducting medium and you put it in the superconducting phase, well, some of them do this, most of them don't, but you can, if there are superconducting media that spontaneously generate magnetic fields. And the spontaneous generation of magnetic fields spontaneously breaks the time reversal symmetry. And the residue of time reverses symmetry, what's left over after you spontaneously break it, is an operator that squares to -1. And so there's perfectly good, and it's like an integral of motion because it's a superconductor. I mean, it's perfectly good operators out in physical systems which square to -1, real operators. And you can't assign a real number that squares to -1. So what do? You do something that I think Cardano had done. I don't know why there's a double R in Cardano's name, which is you just invent a new type of number. You call them super numbers, except that you didn't call them super numbers. You call them complex numbers because they're really, really crazy complex. They're not real. They're just crazy imaginary and complicated. And all a complex number is it's a pair of real numbers. It's a Z2 graded number. And when you multiply two complex numbers, adding is just adding, but when you multiply two complex numbers, you just add the gradings, and then you do like one little funny sign thing, that if both terms in the multiplication happen to be odd, you put a -1 in some. So I want you to think this is sort of formally the same. It's not exactly the same, but it's of the same flavor as the way I define supervector spaces. I just took Z2 graded things, did the obvious multiplication, but then fudged the signs. Maybe later I have to fudge a scale or something. And now you can ask, is this good enough? Like, I needed to add a square root of -1. Is that good enough? And the answer, actually slightly surprisingly, is yes. So Hilbert-Mills-Stollen says that if you have a commutative algebra, which is not the zero algebra, and not too crazy big, then it does have a homomorphism to the complex numbers. And this is equivalent to saying that the complex numbers is algebraic. But this sort of Mills-Stollen-Satzian way of saying algebraic closure is a way that works very, very well as you transport around. So that's the way. So what I'm hoping to convince you so far is that there's like this sequence, this sort of this zero-dimensional thing about complex numbers, and then the vector spaces. The Deligne theorem was saying that the supervector spaces are somehow algebraically closed, but in the world of categories and particles rather than in the world of algebras and So now that we've done 0 and 1 dimensions, I can start to tell you about the new stuff. This is all, well, Hilbert-Mills-Stollen was like 100 years old, and Deligne's theorem is maybe 20 years old. So what have we done more recently? So let's go up in the dimensions. So in addition to local observables and point-like excitations, quantum systems can have extended excitations. But so as a good example, like as far as we know, the fundamental theory of nature doesn't have any extended excitations. It's just a theory of particles. But all sorts of effective models, all sorts of low temperature effective theories do have extended excitations. And a good example is that you might imagine a crystallization process. And you might imagine a material that wants to form a cubic lattice when it say freezes. But you could sort of take a beaker, like what am I doing? You take a beaker of sugar doesn't actually want to form a crystal lattice, but imagine that sugar does. So take a beaker of sugar water at very high temperature and slowly lower the temperature. This is sort of, I hope you've all made rock candy sometime in your life, because that's what this is. So you slowly lower the temperature and you end up with a supersaturated solution. But if you seed the crystal somewhere, then a crystal can grow out. So now what I want you to imagine doing is take the beaker and seed it all the way around the edge of the beaker in a way where like there's a slight mismatch of the crystal seeding that you start. And then the crystal will grow into the middle of the beaker, but it'll get forced to have a defect where this cubic lattice fails to line up when it sort of tries to freeze out. So that defect, like that stresses the system. It's not in the lowest energy state it could be in. And the defect might try to move a bit. If the defect has a kink in it, the system would prefer to straighten that defect out to sort of make less stress, less total strain. So the defect is some dynamical extended object. But the defect can't completely be removed because that would take a humongous amount of energy. We'd have to rearrange the crystal all the way out to the edge of the beaker, which is, at least in a low temperature, sort of once I've lowered the temperature, very, very far away from what the defect is. So this is sort of example of an extended object. And now you could ask the same question. Can I consistently assign something to extended objects? And what should I be assigning? And you can go higher. There's the word grain just means extended that's above string. So physicists have like instantons, particles, which are one-dimensional, strings, which are two-dimensional because it's one in space plus the time dimension, and grains, which are higher than. And now I have to sort of start talking about the language where you impose this problem. So to talk about extended objects and their fusion this is what higher categories are for, in some sense, or at least this is one of the things higher categories are for. I'm not going to right now try to tell you what a higher category is. It's something that's like the next thing after, like it has, a higher category is a thing that organizes the algebra of objects of different dimensions. And it organizes it the same way that associative algebra organizes the fusion of particles on a line. And so just from sort of the fact that, just from that description of higher category theory, you might believe me that it's the right language for organizing the fusion of extended objects. So the question then becomes the following. It becomes, is there a higher category, an n category for every n, so that is there a higher category so that who can consistently where I can consistently assign kind of internal states to every extended object in a quantum system. And I should probably be like, my extended object should be sort of low, like there should be enough ambient dimensions where I have good commutative for this to be an interesting problem. Right? I don't want to talk about an odd in this instance. And now I can tell you our main theorem. Of course, I wouldn't be here talking to you if we didn't think the answer was yes. Our theorem is a qualified yes. The theorem is that if by n category you mean semi-simple n category, then the answer is yes. So implicit in this, in what I just told you, is that we do have a good theory of semi-simple higher categories now. And one of the things we did in getting towards this theorem was to sort of spend the last few years actually developing. This is why I've been thinking about semi-simple higher categories and doing a lot of work on. But those of you who know me know I've sort of spent the last few years sort of figuring out, like, what does idempotent mean? What does semi-simplicity mean? It's all for this result, so that we could state this theory.
Do you know whether the answers ever met?
So the Hilbertsville-Schoensax was wrong if you allowed algebras that were too big. It was wrong for if you had, if you have like an uncountably generated associative algebra, it might not have the homomorphism back to the complex numbers. If they're countably generated associative algebras, it still does, but for uncountably generated, it never fails. And anyway, Hilbert only said it for finitely generated algebras. And Deline's theorem needs an even stronger finiteness condition than Hilbert does. There's some actually subtle conditions in the sort of size constraints in Deline's theorem. Semi-simplicity is a size constraint. It is too strong a size constraint. We are very aware that semi-simplicity is like, there should be a better theorem and we are sort of trying to figure out what that better theorem is that goes beyond the semi-simple case. But at least we're like, okay, this is a size constraint. It is like of the pattern of these other Milch-Stollen-Stutz conditions. It's insufficient. I do know a two-category. Well, I haven't told you what our higher categories are, like what our answer to this question is. I do know a two-category who doesn't have a homomorphism to our answer. It's like a good two-category if you're a representation theorist. And it annoys me. It's like not semi-simple, but it's not that far from being semi-simple, and I haven't figured out what to do about it. But that's something we can talk some other time, and I'll tell you the details of that. Okay, so this was the theorem, and I gave the statement faster than I thought I would, so let me, which gives me more time than I thought. I'm now going to sort of slowly move into sort of giving a sense of what the methods are that we use to build this thing. I won't give all details right now, but I want to kind of give a flavor of the sort of different ingredients that we had to do with this. So I'm looking for, as I said, I'm looking for sort of algebraic closures in some sense. It's a higher algebraic, a higher categorical version, but it is at the end of the day an algebraic closure. So how would you go and try to find an algebraic closure? This could be hard. You might not have good ways to build an algebraic closure. And the reason you might not have good ways to do it is because in undergraduate algebra, the way we teach people that algebraic closures exist is by running a Zorn's lemma argument. And the Zorn's lemma arguments tend to fail badly in higher categories. And there's a reason for them to fail. It's because the algebraic closure is not unique. Like, this is something I hope you emphasize to your undergraduates. The algebraic closure is unique up to isomorphism. But it's not unique up to uniqueness. That's the whole point of Galois groups. And the failure to be unique up to unique isomorphism is, from a category theory, from a higher perspective, a failure of like uniqueness. And it makes it really hard to find. It means that the algebraic closure doesn't satisfy a good universal property. Things that have a universal property you can often kind of identify, but the algebraic closure is not of that type. And the Zorn's lemma avoids this problem, but it avoids it in a sort of very set theoretic way. It doesn't avoid it in a way that works well in higher algebra. So instead, there's a different way to do it, which is just guess the answer and then check if it's algebraically close. Okay, or at least make a very educated guess of the answer. So now we need to kind of have some heuristics, some guidance for how to find this educated guess. So okay, I want to find an algebraic closure. I'm going to sort of set that problem aside and try to find the easier one. Let me try to not find the algebraic closure. Let me just try to find the Galois closure. Let me hope that my algebraic closure is Galois over my base fields. This is something that might be true and might not be, but I can hope it. And I could go look for the Galois closure, the universal Galois extension, and then maybe it'll magically be in the universal algebraic extension. That's a good hope. So how do you find Galois extensions? I need to find the universal one. Well, representation theory can help. So here's a nice fact in the first course of graduate algebra, undergraduate algebra, somewhere in that range, is that if you have some fixed field that you care about, whose Galois closures you want, whose Galois extensions you want to study, and you could ask yourself, what are all the Galois extensions of your field with Galois group G? Fix a group. So I'm not going to right now look for the universal one. I'm just going to look for all the ones with a specific Galois group. Well, what you can convince yourself is that the Galois extensions of a field with Galois group G are the same. Okay, obviously you know that this is the same, of course, as surjections from the absolute Galois group if you had access to the absolute Galois group to your group. And surjections are too hard. Category theorists are not very good at telling which maps are surjections and which maps are just jections, and neither surjections nor injections. And so let me just look at all maps, and that one's an easier problem for me to handle. And what you can show, and this is the exercise for those of you who haven't done it, is that maps from the absolute Galois group to your group are the same as symmetric monoidal functors from the category of representations of your group back to the category of vector spaces.
Symmetric what functors?
Sorry, symmetric monoidal. Functors that play well with all of the tensor products. There's a tensor product on representations. I want a functor that takes the tensor product of representations to the tensor product of vector spaces. Of course, you know a functor like this. You can just write down the underlying vector space of any representation, and that is the tensor product of vector spaces. That corresponds to the trivial map, the constant map from the absolute Galois groups of G. I am telling you that there can be other such functors. And this is, in fact, an identification. So this seems like a good strategy. I mean, in fact, you can even run this around. So if the functor that corresponds to, if you have a functor and you want to know which Galois extension it corresponds to, you reach inside of the representation category. There's a specific representation called the regular representation. And this representation is a commutative algebra in a sort of G equivariant way. And you apply your functor to it, you get some commutative algebra in the category of vector spaces, which as a representation is the regular representation, but as an algebra might not be the underlying vector space of the regular representation. It's some other algebra structure on the regular representation. It's off by some scalars, which is really what we were seeing before. Like the complex numbers look like Z2 graded vector spaces, except they're Z2 graded numbers, except they're off by some scalars. And that algebra is the corresponding Galois extension. So that's how this works. Unfortunately, this is actually useless for finding Galois extensions, because it turns out in practice that you have no way of working out what all the functors are between a category like rep G to Vec without just using the other side of the problem. Okay, so that was a good guess, but it wasn't good enough for the problem I'm trying to solve. Well, okay, so I said I hoped that my algebraic closure was actually magically Galois, and then I didn't have to find the universal algebraic extension, I could just find the universal Galois extension. So let me add another, even more fanciful hope that's like really unlikely to be true, but I'm still sort of out searching the world. So let me hope that my Galois group is actually abelian for sort of no good reason. And now I can start doing the problem. So let's just look for abelian extensions. And the advantage of looking for abelian extensions is that I'm really, really good at the representation theory of abelian groups. Like representation theory is hard, but abelian representation is not that bad. And for example, I'm especially good at the representations of abelian groups when my ground field has enough roots of unity to accommodate the the orders of elements in my group. And then I know exactly what the representation theory looks like. I know that there's a whole bunch of invertible representations. All the irreducibles are invertible. I know how many they are. I know how they fuse. And it's just the dual abelian group. I mean, it's like a sort of very accessible problem. And then I really can run this game. I can ask, what are all of the maps, all the nice functors from representations back to vector spaces? But because I'm really good at representation theory of abelian groups, I know exactly well, to tell you a functor is to tell you what it does to the simple objects. And maybe I'm in characteristic not dividing the group too. Like maybe not as good as many goodness properties as I can think of to solve this problem. So then I just have a whole bunch of simples. They're all invertible. And to tell you the functor, I just have to tell you what to do with the simples and some linearity data, some sort of ways that it lays well with tensor products. So that's just a map from the group of simple objects to the category of vector spaces. Well, the group of simple objects is a group, which means it's only going to probe the invertible vector spaces and the invertible maps between invertible vector spaces, because it just can't do anything else. And so I don't have to care about all vector spaces, I can just care about the invertible ones. And the invertible vector space? Well, there's an invertible vector space is a vector space that when you tensor with another vector space, you get the one-dimensional vector space. And I bet you know what dimension your vector space has to be. But the invertible vector space has some automorphisms. So the category of invertible vector spaces is not the trivial category, but it almost is. So I've really dramatically simplified my problem. Rather than this hard problem in representation theory over a non-algebraically closed field, I've given myself an easy problem of working out what are all the maps from some abelian group I know to some other abelian group I know, with some like a little bit of category sort of in the way. But like I said, it's like homotopy theory in the way. It's not as hard as like there's nothing non-invertible anymore. It's just a problem in homotopy theory. So the way this really works, the fancy words are that if you have is a sort of what's actually called a spectrum of your field called the Picard spectrum. It's just an Eilenberg-MacLean spectrum, if those were words that mean something to you. But you could do this over any ring, and those of you who care about commutative rings know what the Picard group of a ring is.
So sigma is suspension.
Sigma just means suspension. Sorry, this notation. Sigma means suspension, H means Eilenberg-MacLean, and K cross means K cross.
Some reason I looked at sigma and everything before thought it was a direct sum. Trying to figure out.
Oh. This I just meant suspension. I mean, I actually hate the notation sigma for suspension, but it's what the homotopy theorists use, and I don't ever actually use it in my own. Like when I'm writing, I just put like brackets with numbers in them for degree shifts, but I think that's a better notation. Anyway, the point is that I've translated this problem into a problem that's secretly a problem in stable homotopy theory, where there's sort of better tools to study. It's a problem now a problem in homological algebra. It's not a problem in representation theory anymore. And there's better tools in homological. It becomes a more computable problem. So what I'm telling you to summarize is I'm telling you that, that abelian Galois extensions with Galois group G are the same as spectrum maps from the Eilenberg-MacLean spectrum for the dual group to this spectrum called the Picard spectrum, whatever those are. And to the extent that you can understand what the Picard spectrum is, you could compute the space of these maps. And then if there is a universal abelian Galois group, which we know there is, a universal abelian Galois extension of fields, but if there is one, then it's the universal such map like this. And it corresponds to the universal map into the Picard spectrum from an ordinary group. And the interesting thing is, this guy is a spectrum. This guy is just an ordinary group. And so the question becomes that. But anyway, that's what it is. So now I'm in business. So now I can start looking for at least the universal abelian extension of my object. So let me step back and say remind the problem that I'm trying to solve. What I'm really doing is I sort of try to build this higher category inductively. I started with the real numbers. I looked for the universal extension of it. It happened that the universal extension of the real numbers was abelian. It was sort of magical, but it was true. And then I got the complex numbers. And then it was really easy for me to start with the complex numbers and get the category of vector spaces over the complex numbers. And then I looked for the abelian, the universal extension of it. The super vector spaces happened to be an abelian extension. No reason, just happened to be. And now from the category of super vector spaces, I can sort of do a sort of naive thing that sort of is like taking vector spaces of a ring, or the modules for a ring, and then sort of category, using one category level up and look for the universal extension, and so on. So I'm doing this sort of step by step. And what I told you was that, and so curly A was just like the thing whose algebraic closure, whose abelian enclosure I'm trying to find. And I told you that abelian extensions of it, whatever it is, are spectrum maps into some Picard group, and I want spectrum maps from an ordinary group. Just looking for sort of maps from an ordinary. And I will remind that like there's two problems with this. First of all, a priori, there might not be a universal map into a given spectrum from like this is an interesting problem that nobody in mathematics has told me the answer to in general. But like when does a spectrum have a universal map in from an abelian group? There's some conditions where it is, like if the spectrum just happens to be an abelian group itself, then you just take the abelian group and it's universal. But hard spectrum of a field is already an example that shows you that you can go beyond that. And also let me remind that the algebraic closure might not have actually have an abelian extension a priori. And our theorem is that in fact we can solve both of these problems. This is what the meat of our results says. Our theorem says, first of all, I'm doing this very inductively, so if I already know that I started with somebody who is algebraically closed at its height, or its amount of complicatedness, categorical complication, that gives me that tells me some information about the Picard spectrum of the next person. And then we also use some sort of things about, like, somehow magically use the fact that the integers have curl dimension 1, which helps us. And with these two ingredients together, let us prove a sort of general, like it's like a computation-free proof. It's just sort of like this guy's algebraically closed, and therefore something about mapping into it. There's sort of a curl dimension argument, so therefore something else. And together, these two do tell us that there is a universal abelian group that maps into this Picard spectrum that I happen to care about. And I'm not going to say more about how that proof goes, but that's the sort of the basic idea. And so at least, so then that does tell you that there's a universal abelian extension at the next level. And then the last theorem is that actually this universal abelian extension is exactly what I was looking for. It turns out it's algebraically closed. Like it's no Schillen-Satzian. And so now you could ask, like, hey, why did you hope? Like, how could you have? This seems way too optimistic. Like, how could it have ever been that the algebraic closure was an abelian at Galois extension? And well, maybe you weren't so surprised that the algebraic closure was a Galois extension, but why would it be abelian? And the answer is because secretly this is like the Galois group is secretly a sort of higher homotopy group is what I'm really probing, and you know that higher homotopy groups are sort of abelian for stupid reasons. Like it was this weird thing, like when they first invented homotopy theory, they got really excited. When they first invented homotopy groups, it was like really cool because homotopy groups were this way of studying spaces that move them into algebra, and groups are really rich, and so you got all this information out of space from its fundamental. And then it wasn't like that hard to guess the higher homotopy groups, so you guess their definition once you know the definition of a homotopy group. And it was sort of, like historically, quite a disappointment when somebody pointed out that higher homotopy groups were all abelian. Because abelian groups are so darn boring. Like, at least finding the generative abelian groups, you know all of them, you can just write them like, one of our every year qualifying exam problems is just like, tell me every finite abelian group of order something, and we just change the number. Like tell me all of them, so well anyway, but there is more information in homotopy theory than just the abelian groups. Fortunately, there's how they're put together. So let me say a little bit more, which is to actually kind of now compile all of these extensions. So
Question, you just showed that there is you've taken this algebraic, there is a universal Galois extension,
yeah,
and it's algebraically closed.
Yeah.
But then is it universal amongst things that are algebraically closed, or do you have some kind of thing showing you it is the algebraic closure?
Well, remember that my definition of the algebraic closure is, my definition of algebraically closed is that it's non-Schwann-Satzian. Right, so you could ask, like, so you could ask this sort of question, like, how do you know that two algebraic closures are isomorphic? And the way you know it is, okay, well, this one's non-Schwann-Satzian, so that one maps to it. That one's non-Schwann-Satzian, so you have a map in the other way. So at least you do have maps in both directions, and you could hope that those maps are going to be an isomorphism. Well, what do you need to show? Well, I mean, of course, they're not going to be inverse to each other. They'll at least be off by the Galois groups on either side. But you want to show that the compositions in both directions have the property of being, like, what do I say? If FG and GF are both isomorphisms, then F and G are both isomorphisms. And so, what you need to actually then argue is that for your putative algebraic closure, all of its endomorphisms are actually isomorphisms. And this is like a fact that you can, like, it's not actually true, by the way, for a general field. Like, there are perfectly good fields that have endomorphisms that are not isomorphisms. It's a good exercise to sort of define them. So that's the type of thing you'd have to check, and it is true in our context. It's not even that hard in our context. I think if I were to try to move into this sort of what I really want to do about like getting past the semi-simple case, then I would have to sort of start to think about that problem exactly. I have a little bit more control about it, than I told you. But it was a good question.
Yeah.
So I guess one sort of question is, do we know what the absolute Galois are? They LZ2 again, or are they?
Great. So this was going to be my next slide. So I was going to hint at this in the next slide. It's exactly the next question, and the answer is they are definitely not all Z2. That's a sort of. So let me start to tell you how one would compute this. So I have what have I done? I started with the real numbers. I did a sort of first a Galois extended to the complex numbers. That was the algebraic closure in the world of uncategorical algebra. It's still a Galois extension. It's just not the algebraic closure anymore once I go to categories. I Galois extended to supervector spaces, and then I keep Galois extending. Something that every student gets wrong the first time that they teach Galois theory is that the composition of Galois extensions is not necessarily Galois, but it often is, and it is under some mild condition, which is holds in our case. So I can sort of totalize this tower and get and so I have some infinite sort of sequence of Galois extensions, and that's the thing whose Galois group I want to study. And each of these extensions was sort of in its own homotopical degree when I totalized the thing. So actually the total thing is like if all I care about is the homotopy groups of the sort of categorical absolute Galois group, the higher absolute Galois group, then this is just a step-by-step problem I'm doing. So that's what I'm doing. I'm looking for the kind of right. So this is the next question. I want to compute the sort of the homotopy groups of the total of the algebraic closure. So this is just the homotopy groups of this extension I told you about, of the sort of one-step extension. And again, the one-step extension was just something completely controlled by a Picard spectrum. And so now I can, like, again, it becomes a problem in stable homotopy theory. It's understand this Picard spectrum and maps into it and that kind of thing. And now I'm just going to tell you kind of the answer. So when you actually unpack who this Picard spectrum is and who the universal thing that maps into is, what you find out is that you're doing the same problem as the following. You are also asking the question of what are all invertible n-dimensional phases of topological theories with a topological boundary condition, and known in the semi-simple ways. And this is actually formal. This is a formal. The reason why this is formal, so Picard spectrum, as I said, was something about invertible. That's what this word invertible means. And it was about invertible modules. And the fact that it's a module is what gives me a boundary condition for it. And the rest of the translation is this sort of what's called the cobordism hypothesis that lets me study any category at all is a category of topological field theories. That's what the cobordism hypothesis sort of tells is the says. I always get to pretend that I'm doing physics if I want, and I can secretly do hyperalgebra. This is still pain. Okay, so this is the same problem. Understand the n-dimensional invertible phases that emit a boundary condition. And now I'll just tell you how we do it. So what you want to do is you want to then start. So I have some invertible phase with some possibly very complicated boundary condition. The invertible stuff, that's a pretty simple thing. But the boundary condition might be very, very complicated. So what I want to start doing now is to study this joint system. I want to start simplifying the boundary in a way that doesn't change the invertible system. And it turns out there's some methods to do this. They go by many, many names. They're called condensation, and they're called gauging and ungaging, and they're called everybody has a name for it. And there's a sort of pretty good simplification procedure that we've kind of understood that actually ends up to us feeling like surgery for manifolds, if you're a topologist and heard of surgery for manifolds. And it really does. So the way it works is that when you surgery a manifold, what you do is you pick up a manifold, and one of the problems in surgery theory is pick up a manifold and see if you can simplify it to being a sphere. Well, that's too hard. Let's see if we can simplify it to being a homology sphere. So let's see if we can sort of simplify in a way that kills homology. And the way you do this is you reach inside the manifold and you say, well, the low-dimensional homology cycles, if I surgery along any specific homology cycle, it'll kill that cycle, and then it'll produce some other junk possibly. But if the cycles are all low-dimensional, then I can surgery along all of them simultaneously because they can just decouple from each other. And I can kill all of the low-dimensional homology. But it's a manifold. If you kill low-dimensional homology, you also kill high-dimensional homology. And so you can sort of concentrate the homology in middles of it. That's how surgery works. It's the same thing we do. We have a sort of surgery description for boundary theories. What we do is we reach inside the boundary theory, we look at its extended objects. The low-dimensional extended objects, you can pull up, sort of disconnect, and you can surgery them away. And you can start to concentrate the boundary theory in some kind of middle dimension. So what we end up with is a surgery description of the Galois group. What happened to my pointer? There we are. And it feels very, very similar to surgery of manifolds. It's specifically, for those of you who know this stuff, which I didn't until I started doing this project, it presents the Galois group in a way that looks very, very close to the group that's called PL. This was a surprise to us. People who study topological field theories get very used to thinking about the orthogonal group. The orthogonal group is the wrong group. Piecewise linear group turns out to be the right thing for topological field theories.
What's the piecewise linear group?
It's the group of, so the orthogonal group is homotopy equivalent to the group of diffeomorphisms phi. And the piecewise linear group is the group of piecewise linear automorphisms phi. It's some infinite dimensional topological group, and I really only care about it as a sort of homotopy type. I'm just trying to present a homotopy theoretic description. It's not a Lie group. It doesn't have a Lie model. I mean, it's in low dimensions agrees with the orthogonal group because every low dimensional piecewise linear map can be smoothed, but in high dimensions it doesn't. The piecewise linear group actually turns out to, in homotopy theory, turns out to be a really, really complicated thing. It is as complicated as the homotopy groups of spheres. in a sort of precise way. Anyway, let me give one sample corollary of our computations. This is just like from the computations that we did. I'm not going to say how this works, but from the computations, from this like explicit description that we have from surgery, an example corollary is the following. If I have a gravitationally anomalous theory with non-trivial anomaly, it's necessarily gapless. Or let me say that equivalently, if I have an invertible phase, and this is all in the sort of world of framed, so there's no Lorentz invariance at all. It's just, so in condensed matter systems, you don't have Lorentz invariance. Like condensed matter systems are defined on a lattice. You cannot continuously rotate a lattice. There's no reason to care about Lorentz invariance if you're doing kind of actual like material science. So the same statement translated over is that if I have an invertible phase in the bulk, so if invertible phases have no local excitations at all, like no anything, there's no observables or anything. You can ask, what about the boundary? Like the material has to end somewhere. What's the physics on the boundary? Well, there's lots of possible physics on the boundary because it depends on how serrated your scissors were when you cut the edge of the material. But the theorem is that the boundary system is necessarily conducting. It's necessarily a gapless. The materials, like, what you imagine is that if you have a material might have some excitations that have some like amount of energy it takes to do the excitation, and if that energy is above the energy that you have access to, then you can't like push signals or current or anything through the material because you'd have to kind of use a lot of energy to do that. Whereas a gapless material, a material that has very low energy excitations, it's easy to just sort of excite it and conduct current through the material. So this is the sort of what the topological insulator stuff is about as far as I can tell. Yeah, so and there's one exception, which is that if the bulk theory happens to be an Arf-Kivare invariant, then it does admit a gap boundary condition and a very hard, like I think this was a 200-page paper, hard calculation of Hill, Hopkins, and Ravenel says that there are very, very few non-trivial Arf-Kivare invariants. You can write them down in any dimension. In any dimension, it's 2 mod 4, but they're all trivial except for in these 6 dimensions. So I think I should stop here, and thank you for your attention.
Is there significance to the fact that these numbers are too shy of a priority?
Yes, but that you should read their paper. No, like this is just some like this is. Yeah, I have nothing to say about this theorem except that I can quote it.
So you mentioned that, how to start computing these like Galois groups,
right,
and that they're in the spectrum. What is the next one?
Right. So
Z2.
So because, as I said, it looks a lot like the homotopy groups of PL, which you also don't know. But the homotopy groups of PL look at first like the homotopy groups of O, which you do know. The homotopy groups of the orthogonal group, it goes Z2, Z2, 0, Z, 0, 0, 0, Z. And then it repeats. Homotopy groups of PL don't quite do that. They pick up pieces from the homotopy groups of spheres and from a few other places. But at first they look like that. And the other difference is that instead of a Z, you don't, so, Galois groups should never have Z factors. Galois groups you immediately can reject Z as a factor in a Galois group because Galois groups are profinite. And what we actually see both in PL itself, the Z factor is coming from something called L theory. It's from the fact, so I told you that when you try to concentrate a manifold to middle dimension, you end up with sort of something left over in middle dimension possibly. If there's no middle dimension, half the time there's no middle number between 0 and n, and then you don't have anything to do. The other half the time there is a middle number. And what you end up with left in middle dimension is you end up just with the middle dimensional homology and a homology pairing on. And you can continue to surge your away if your homology pairing has, so that's always a non-degenerate pairing, which is either symmetric or skew-symmetric, depending on something about the dimension. And you can continue to surge your away as long as you have isotropic subgroups. And the definition of L theory is it's the group of non-degenerate pairings of prescribed signature, modulo isotropics, modulo sort of, modulo condensation, if that's the language you want to, or whatever you want to call any language. And for the actual thing that topologists, manifold topologists do, the types of pairings they're looking at are pairings on homology, which is typically, homology of a manifold is a finitely, like, if you're just in middle dimension, there's going to be some finitely generated Z mod, like some free Z module, say Z to the n or something like that. For us, we're doing a slightly more finite version, and so our groups that we get in middle dimension are finite groups with a non-degenerate pairing, but the rest of the story goes through. So it's a slightly different L group. It's some finite weight group. So that's the main difference. So yeah, so to answer your question, Z2, Z2, 0, and then a weight group, and then some other stuff. And if you guys, if y'all will like permit me to answer one other thing about this. So that would be the story, is that it would be like, it would look like PL, except that like the story is almost that the Galois group is PL, except that every time PL has an infinite weight group, we put in a finite weight group. And otherwise it's the same. At least it's the same in homotopy. We haven't finished the problem to do it at the spatial level. We're close. That's the part that we have, but we're still working on to do it at the level of space. But at the level of homotopy groups, it's just a theorem. The homotopy groups of the Galois group are the homotopy groups of PL, except that except it's a different L groups that go into it. And this is true except for in dimension about sort of in dimension 4. And the reason why is because surgery theory just breaks in dimension 4. 4 manifolds are weird. 4 manifolds are weird in all the ways that
Sorry, excuse me, I might have the wrong reservation, but I thought, I don't know if you guys are almost done, but maybe we have the wrong room, but I thought we had this one for 5. I'm not sure if I'm in Cockentall 240.
Yeah, this is Cockentall 240. We have a colloquia in here.
It'll be just 5 minutes.
we
Oh, yeah,
won't be out in.
Okay, sorry, I just want to make sure I was in the right place. Thank you.
So let me just sort of tell you a little bit more topology. Why are 4 manifolds weird? Why does topology have this phase transition in dimension 3 and 4? It's because there are non-abelian knots in dimension 3. If you try to do surgery theory involves taking cycles and pulling them apart. If your middle dimension is roughly 3, those cycles can be badly linked in a sort of non-abelian way. And so to tell you the invariant of cycles in dimension 3 is not just sort of like links in 3 dimensions is not just a homology pair. It's more data, it's less abelian than that. And it also breaks for us in exactly the same way. And so actually the Galois group that we compute in dimension 4 exactly is not the sort of an easy L theory group. It's called the quantum Witt group that some people in this audience might care about. And it's crazy because the quantum Witt group has Z factors in it. And so actually our Galois group just isn't a profinite group. Like our Galois extension is a perfectly good Galois extension that's not a infinite Galois extension. And that's all I can say. Like I don't know, I just shrug my shoulders. So anyway, I didn't mention that.
Question. So you mentioned that you can compute the homotopy groups, and you said said something like you're doing it stage by stage, and so like just sort of pick up things along the way. But are there non-trivial K invariants in between, like talking about connecting them?
Surely yes, in the sense that I believe that the Galois group matches PL, except for in the way I said it doesn't. And in PL, the answer is yes. But I can't yet do that computation. I mean, until like we are on our way to having that computation done. Not that I'd ever be able to write down the K invariants. What I could do is hope to show you that like, there's this map from PL to our Galois group, which is an isomorphism except for in the way it isn't. And then that would be the type of theorem I'm going for.
So your stuff was inspired by like this fermion story, where like just you have these integral degrees of freedom, and you can you have all the nice things you want. You can swap them, you can put them together,
right.
All that. And so of course with non-abelian anyons, there's non-local data.
Yes.
And I know that's not the dimension you're working in, but is there room to expand this for non-local information as well?
Well, I think the answer that makes sense to me, I don't know, because I don't really know what information is, but I do know a little bit of non-commutative algebra. And you would never hope to have a Nullstellensatzian algebra, like to have an algebra which was Nullstellensatzian on non-commutative algebras. That would be, like, of course there isn't a universal non-commutative algebra. And so similarly, of course there isn't a universal graded tensor calculus. The best you could hope for would be universal among the commutative ones.
Okay, if there are no further questions, let's thank Theo again.